And let's do a share screen. It's like the cable is. Do a share screen? Yes, good. Okay, so before we really start, I had some time to look yesterday at your problem set number 3. And it generally was okay, but there were two things which jumped to my mind because I thought they were quite simple. But for some of you, it was not as simple as I thought. Actually, maybe 3 things. So in question number 3, questionnaire number 3, right, the first question, I gave you a few diagrams, and I asked you which one is allowed and which one is forbidden. And specifically, there was one diagram which looked like that. So there was an electron and an anti-quark. They interact via the Z boson, end up with an electron and an anti-quark. And some people have said that this is possible, and I was really disappointed because there are very many reasons why this is impossible. And I think that the common mistake that I saw was that people thought that it's enough that the total quantities are conserved. Now, the issue is that all the quantities, as we discussed, charge, baryonic number, leptonic number, everything, they must be conserved in each vertex. So they must be conserved here and here. If they're not conserved in each vertex, although they are globally conserved, but then that means that this is not allowed. So this was a mistake that some of you made. So I don't want you to make it anymore. So that's one point that I wanted to mention. Another point that I wanted to mention in question number 2, part 1, there was a small typo there, but really small, which rather than writing gamma, gamma goes to E plus E minus, you had to draw a Feynman diagram for that. It was written gamma and then gamma like that goes to E plus E minus. So some of you got confused by that, and for some reason wrote, a diagram that looks like that. Gamma goes to E plus and E minus, right? Now, it's okay to say that there was a typo, but I definitely expect you to know by now that such an interaction is forbidden. And so I took off points, not because you missed a typo. It wasn't even a typo. It was just written like one gamma in words and one gamma in the Greek letter. But this is something which I definitely expect you to realize by now, right? That a photon by itself cannot decay into a pair, and you should realize why. And then some of you made something which I thought was pretty funny mistake in question number 3, which dealt with the Mandelstam variables. And then the second point, so in first point, you were asked to show that S plus T plus U, they are not independent because they depend on the masses, which you did. But then in the second I asked, okay, so how many independent Mandelstam variables there are? So if there are 3 and there is one constraint, then obviously that there must be 2 independent because the third one is determined by the constraint. So for some reason, not all of you did it properly. I don't know, I'm not sure why, but that's quite simple. So that's about your problem set number 3. Okay, that's what I want to say about that. Now let's proceed. So we are discussing Dirac equation. And last time we discussed Dirac equation. And we managed to say many things about the Dirac equation. And the last thing we said, so very briefly, so we spoke about a covariant form of the Dirac equation. We introduced the gamma matrices, right? I wrote down that I can write Dirac equation as I gamma mu d mu minus m psi is equal to 0. Gamma mu are the 4 Dirac matrices. I was asked about the presentation. So yeah, there are several known presentations for the 4x4 presentations for the gamma mu matrices. The ones that are typically discussed, but not in this course so much, is there is a Weyl representation, also called chiral. I will introduce to you today what is chiral, which is easy to work with chirality eigenstates. There is a Majorana representation. Majorana is used for hypothetical particles that are not yet discovered and are not part of the standard model, and that is of fermions who are their own anti-fermions. So spin 1/2 particles who are their own anti-fermions. This is called Majorana representation. So there is a Weyl representation. There is a Majorana. After Majorana, possibly there are more, but they're not normally mentioned. And even these are not really mentioned in this course. These are mentioned in a higher, beyond the not in the introductory course. Yeah. Questions? I cannot hear you. I'm sorry, I cannot hear. Is there anybody trying to ask a question?
Yes, I was. My internet froze. I started to ask, so these different representations correspond to different physical particles?
No, they're not different physical particles. We're talking about all solutions to Dirac equations. It's, well, eigenstates, well, all these particles, well, they'll have certain properties which are not, it's not just the solution of the Dirac equation. We're talking also about if a particle is its own antiparticle, that means that they have to be neutral, right? You cannot have this charge and anti-charge.
Yes.
Right? Yeah. No, it will not be different particles as far as I can see. Well, you know what? I'm not even sure. I need to think a little bit more about it.
Sure. Thank you.
Anyway, we are sticking with the Dirac Pauli representation, which is the mostly used one, Dirac Pauli representation. And no, sorry, it has to be the same particles because essentially it's, we have 4 independent solutions. That's what we show. We have these 4 spinors, and then the Dirac Pauli representation is the easiest to learn the properties of this. So I introduced you these matrices. I showed you direct proof that the Dirac equation is covariant. Then there is introduced the covariant current and the adjoint spinor. I'm not sure that I'm going to have much time to discuss that, right? So we said that J mu, so that's the covariant current. J mu is psi bar gamma mu psi, where psi bar is psi dagger gamma 0. This is a 4 vector. Why this is important? Because this appears a lot of these terms in the vertices, right? When we want to calculate the contribution of each vertex, right, from a Feynman diagram to the matrix element, hence for the cross section, then currents of this type and several other types appear quite often. So that's why that's the main importance. Then we'll talk about, then we have talked about the solutions to Dirac equations. Oh, plane wave solutions, so free particle solutions. Right, we said that we can write down psi of x and t as cu of E and P, E minus I P mu x mu. And then we said that for particles at rest, forget about the particle at rest, then we found the general solutions, which would be the 4 U's, U1 is just 1, 0, PZ over E plus M, and PX plus IPY over E plus M. U2 is 0, 1 px minus I py over e plus m, and then minus pz over e plus m. And these are the two solutions with a positive energy. And we had two solutions with negative energy. And px plus I py over e minus m, and then a 1 and 0. And U4 is px minus I py over e minus m, and minus pz over a minus m, 0 and 1. So these are all solutions to the Dirac equation. You plug this solution and you retrieve back the Dirac equation. We do find that they both fulfill the Dirac equation. They both obey e squared smaller than 0, e smaller than 0. They both obey the e squared is equal, all four of them, e squared is equal to p squared plus m squared. And of course, in the limit where p goes to 0, we retrieve back the four solutions of the rest particle. Okay, this is as far as we did on Tuesday. Any questions before I go on?
Yes, building on my question from last week, I had some time to think about it. So U1 through U4, they're eigenstates of the Hamiltonian, obviously, so they correspond to either particle or antiparticle solution, but none of them are spin eigenstates, correct?
These ones.
If I look at SZ, which is on diagonal 1 minus 1, 1 minus 1, none of these are eigenstates of that matrix, right?
Hold on a second. Okay, yeah, they're not. I'm going to derive it to you later on today.
So that means that as soon as you have a non-zero momentum eigenstate, it is no longer a well-defined spin state?
Yes, that's exactly why we introduced the concept of Helicity.
Okay.
We'll discuss.
Okay. Perfect. Thank you.
Okay, any more? Okay, so we said that Dirac, we tried to find first order derivative, space and time derivatives equation to replace the Klein-Gordon equation. His motivation was to avoid the negative probability densities. To find a solution. Well, we find four solutions. Two of them have positive energy, two of them has negative energy. Two of them have spin 1/2. Two of them have spin, well, all of them have spin 1/2 particles. But what is the meaning of these negative energy solutions? That's basic questions in physics, because in quantum mechanics, as opposed to classical mechanics where we can throw away the negative energy is simply stated they're unphysical. This is not something which we can do in quantum mechanics or in quantum fields. So the negative energy solutions represent negative energy particle states. So that led Dirac originally to think of it in that simple terms. So we have energy levels. This is E. This is what's called Dirac's interpretation. Which is not the way we see it today, but it's still beautiful. So this is the energy, and there are certain levels. And let's say this is E equal to 0. Right? So you have certain levels. This is called the Dirac C. Now, there is a question. So we have a particle, which let's say it has some energy E. Then the question would be, okay, why is this particle staying here and not simply falling to lower energies, right? Because we know that if we have a free particle, you just fall into the lowest possible energy level. And in this picture, these are, infinity, right? So why doesn't it do so? Any suggestion? So according to Dirac, the reason why it doesn't do so is because all these states are already occupied by particles. And because electrons obey the Pauli exclusion principle, they cannot go down below, to states which are already occupied. So in that sense, this E equal to 0 is, in crystals or in solid states, if you learn it, right, there is this thing which is called the Fermi level. Everything below that is occupied, and everything above that is free. So the E equal to 0 is the analog to this Fermi level. Right. Now what happens, right, if we take one of those already occupied states and excite it, give it energy.
It'll go up and vacate the level?
What?
It'll vacate the level.
It will what?
See, a level will be empty. It can be filled now.
Exactly. The level will be empty. So now we have a hole. Now this hole will act exactly the opposite of a particle, right? It's just a hole in a completely filled sea, right? So holes in the Dirac sea, they would correspond to the positive energy antiparticles, of course, with the opposite charge. Positive energy antiparticles. Now, today we know that this is not a complete description, right? Because for one example, we know that, for example, there is anti-particle states for bosons, and bosons do not obey the Fermi exclusion, Pauli exclusion principle. But the idea is there, and it's a beautiful idea. Okay, so this is as far as the Dirac sea. Now about the anti-particle spinors. So, okay, let's just write it down. Go over that quickly. So in principle, we can do all the calculations with the positive and the negative energy solutions. There is no problem. But we don't like to work with negative energies. This will also mean negative momentum. That means also propagating backward in time. Remember, this is the Feynman-Stuckelberg interpretation. So it is much more convenient, rather than working with particles with negative energy, to work with antiparticles, which are written in terms of physical energy and physical momentum, rather than particles with negative energy. It is better to work with antiparticles. Positive energy. Right. So the spinors U3 and U4, we will basically rename them with an antiparticle spinors with the opposite sign of E and P. So I'm going to define V1 of E and P to be identical to U4 of minus E and minus P. And the same for V2 of E and P. Be identical to U3 of minus E and minus P. Because I prefer to work with positive energy antiparticle solutions. Now we can simply do direct substitution in Dirac's equation. And we get the Dirac equation for the antiparticles. For the V spinor would be gamma mu P mu plus M V equal to 0. Of course, the plus is because we had the original Dirac equation was gamma mu p mu minus m u equal to 0, but p goes to minus p. That's why we have the plus m here rather than the minus m. So, and then it's just a matter of simple algebra to repeat exactly the same calculation as we did on Tuesday. And we find the direct solution to be V1 of EP is just Px minus IPy over E plus M, and then Pz minus Pz over E plus M, and then 0 and the 1. And V2 of E and P is just Pz over E plus M, and Px plus IPy over E plus M, a 1 and a 0. Of course, now E is positive, right? So now E is plus square root of P squared plus M squared. Of course, the full solution hasn't changed, right? It's psi 1, 2, x and t, and the antiparticles. Let's put it C here. So V1, 2, E and P, E, I, P, mu, x, mu. All right, this is just repeating the same steps as we did on Tuesday. Now let's look at operators of the antiparticle spinors. Right, yeah, now the wave function have a plus here, right? Before we had a minus. So if we act with the normal quantum mechanic operator of the energy and momentum, we do not get the physical quantities because basically we switch now from E and P to minus E and minus P. So, if we work, since we switched E minus E, P minus P. And if we try H psi dt psi, we get the minus E psi. Right. Similarly, the P psi will be a minus P psi. So we don't want that. If we want the correct sign, we must redefine the operators. So define the operators to get the correct sign. Correct. 1R, 2R. Not sure. Sign. So H antiparticle would be minus I dt. I'm not sure why I use the C here. And P is a plus I nabla. And if you proceed with that, you'll get that the angular momentum operator of the particle is, of course, the opposite to its regular definition for particles. And since the angular momentum has to be opposite, that means that in order for the total angular momentum of the antiparticles to be conserved, in order for the total angular momentum of antiparticles to be conserved, then right H Dirac L plus S equal to 0, then we must have that the sign of the spin operator must also be reversed. Tell me if I understand why I choose those. These are the V's, right? These are fine. Now, remember when we looked at the particles at rest, right? The particles at rest were eigenvalues of the spin, right? So for particles at rest, we had like S of U3 is 1/2 U3, and SZ, of course. U4 rest is minus 1/2 U4, right? This we did do. Now the spin operator for the antiparticle is changed, right? So S V is minus S. So for particles at rest, we get, or for antiparticle at rest, V1 V equal to 0 is U4 V equal to 0, and that means it will have a spin up, right? Because we just reversed the sign. That's why I chose V1 to be equal to U4 and not vice versa. And the same for V2 and U3. That will be spin down. Sorry, that's why I chose that V1 to be equal to U4 and not V1 equal to U3. This, by the way, is exactly what you'd expect in the Dirac interpretation, right? The state V1, right, we interpret as an electron with spin up that is missing from the C. So it really represents a positron with a spin down.
Could you repeat that last part?
Yeah, the V1, right? Sorry. Yeah, in the Dirac interpretation, the V1 is the positron, right? So it's interpreted as an electron that is missing. Right? Did I get confused here or something? No. So the electron with a spin down is a positron with a spin up.
Okay, thank you.
All right. More questions about that? No. No, no. No, no, yes, maybe. Okay, now I want to talk about the parity operator. So we have certain discrete symmetries. I think I mentioned that in the tutorial, didn't I? It was already, was it? Or no? Yes or no?
You've mentioned, yes, you have parity and PNC
Okay,
symmetries.
good. Yeah, there are three symmetries, right? There are many symmetries. There are three discrete symmetries, PCT. Now, the importance of the P, the parity, this discrete symmetry, the importance is the fact that it is conserved in all electromagnetic interactions, so QED, and also in all the strong interactions, all the QCD, but it's not conserved in the weak interactions. So if we, right, so we want to understand why this is so we have to do the parity transformation properties of the Dirac spinors, which I want to do now. And I want to identify the corresponding parity operator that acts on the solutions of the Dirac spinors. Right? So parity is conserved in QED, QCD, but not in weak interactions. Okay, let's look what parity does to the Dirac spinor. So remember that parity reverses the spatial coordinates, but not the time coordinates. So under parity transformation, so parity transformation, what it does is take R to R prime, which is minus R, and T goes to T prime, which is T. Right? Now that's what it does for the space. Now for the Dirac spinor has internal degrees of freedom, right? It has the spin. So the action of the parity on the Dirac spinor is not so trivial because of this internal degrees of freedom. Nonetheless, it's not that difficult to derive it. So, and by deriving it, we'll deduce how the parity operator looks like. So Dirac spinor has internal degrees of freedom, right? Okay, let's see. Let's calculate the parity operation. On the spinor. So let's assume that psi is a solution to Dirac equation. So we know that I gamma 0 dt plus I gamma j dj minus m psi is equal to 0. Psi solves Dirac equation. And that's Dirac equation. Now psi of course is the wave function, which is a solution of the Dirac equation. So I'm going to act on this wave function with the parity operator. So I take psi, which is R and T, right? And I act on with the parity operator, and I get another wave function, which I call psi p of the new coordinates, right? So p, this is the wave function obtained by acting on psi with the parity operator. P. Now, the new wave function, psi p, must also satisfy the Dirac equation, which is written in the new coordinates, right? So psi p satisfies, right? So if I write down the new Dirac equation, it will be I gamma 0 dt prime plus I gamma j dj prime minus m psi p equal to 0, right? This is the Dirac equation in the new coordinates. Right. Now, if I act on psi p with the parity, what do I get? What do I get? Well, guys, answer. What do we get? Oh, come on.
The original psi?
Of course. Psi is a wave function, right? There's a spatial part, it has an internal part. Okay. Of course, I get the original psi, right? P psi p is just psi. And this psi, of course, satisfies the Dirac equation. I'm going to put that equation right here written. Now I'm going to write down, this is the Dirac equation. So it must satisfy the Dirac equation, I gamma 0 dt plus I gamma j dj minus m p psi p is equal to 0. I just wrote down again the Dirac equation. Yeah. So now I'm going to multiply this by gamma 0 from the left and express the derivatives in terms of the new coordinates. Right. So I get I gamma 0 dt, but dt and dt prime are the same because the time is not changed. Right. Now I have right, dj will be minus dj prime. So I have a minus here, I gamma 0 gamma j dj prime. And here I have a minus m gamma 0. P psi p is equal to 0. Now I can use the anti-commutation relations. Gamma 0 gamma j is minus gamma j gamma 0. To write this down as I gamma 0 dt prime plus I gamma 0 dj prime minus m gamma 0 p psi p equal to 0. Now I compare this equation with the equation that I marked here with the red. And I see that I get the same equation if what? If what do I need to get? What do we need to get? It's not really hard, guys. What?
That the wave function psi is 1 divided to gamma 0 psi p?
No, it's simpler than that. I have the same wave function, psi p, in 1 and 2, right? It's the same wave function. With psi p here and psi p here. I'm actually looking for a way of to describe the operator p, right? So if I write down gamma 0 p is equal to 1 or proportional to unity, because anything which is constant, I can it's a 0 in the right-hand side, then I get the same equation, right? Gamma 0 is a matrix which is made of constant numbers, so it commutes with the derivative. Right, I is of course the 4x4 identity matrix. Now, what do we know about gamma 0? Gamma 0 squared is I. What do we know about p? What is p squared?
Also I.
It's also I, right? So we have two possibilities really. Either that p is equal to gamma 0 or that p is equal to minus gamma 0. Now, this is a matter of convention. Of course, the convention is to choose P is equal to gamma 0. That's what we're going to use. Which means that under parity transformation, so conclusion, right? Under parity transformation, the form of the Dirac equation is unchanged, provided that the Dirac spinors transform as psi goes to P psi, which is gamma 0 psi. If this happens, then the Dirac equation is unchanged. It's not affected by this parity transformation. If then the form of the Dirac equation is unchanged. So we just got the intrinsic parity of the fundamental particle, right? It's defined by the action of a parity operator on the spinor of the particle at rest. So the intrinsic parity right, you obtain by acting on the particle at rest, obtained by acting with P on a particle at rest. Right, P U1 is gamma 0 U1, which is just 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 minus 1. And then if I choose U1, this is just U1. And the same PU2 is just U2, PU3 is minus U3. Or this is, so rather than that, I'll just write down PV1 is minus V1, PV2 is minus V2. So intrinsic parity of fundamental spin 1/2 particle is opposite to the intrinsic parity of fundamental spin 1/2 anti-particle. Which is quite cool. For example, right? For example, right? Since parity is a multiplicative operator, right? If we have a system composed of 2 particles or n particles, we must multiply the intrinsic parity, right? So if we have a system of an F, a system of, let's say, F bar, right? Mesons, meson and anti-meson. Sorry, yeah, just meson, sorry. Quark and anti-quark. And the parity, right? Since we have opposite intrinsic parity, then it must be a -1. But then we must also have the parity of this is the intrinsic parity, but we also have the parity of the space, spherical space component. This will be the -1 to the power L. So overall we have -1 to the power L plus 1. This is intrinsic. This is the spatial part of the wave function. This is the spherical harmonics. YLM. Theta and phi. Right. And L is the orbital angular momentum. So in the ground state, right, for example, right, if you look at pions, there are bound state of mu d bar or du bar, etc. Right? Being in the ground state, then they have L equal to 0. So the intrinsic parity of pions must be negative. All right, questions?
You talk here about the system of fermion and anti-fermion. And you mean it does not have to be the same fermion, right? So it's one fermion, one anti-fermion, but not specifically the same fermion.
Yeah, pions is a bound state of a fermion and anti-fermion.
But they are bound state of yes, up and anti-down, and not like not essentially an up and an anti-up, or down and anti-down.
Pi 0 would be, right? It could be a.
But this is true, so that's what I'm asking. This is true for not just for pi 0, but also for pi plus minus.
Yeah. I just wrote down the pi plus minus.
Yes, okay.
The pi plus minus. Okay. So spin and eliciting. It goes back to the question that one of you asked at the beginning of this lecture. So we've seen that for particles, it's the particles at rest, right? Then the spinors U1 and U2 are eigenstates of the spin operators, right? For particles at rest, right? We have that U1, U2 are eigenstates of S Z, right? S Z, which is 1/2 sigma Z, 1/2 sigma Z, 0, 0, sigma Z, 1/2 1. So obviously U1 and U2 are eigenstates. So they can represent the spin up and spin down, right? But as I was asked, right, obviously, one of you noticed, obviously this is not the case in the general case of particles which are not at rest, right? If the particles move somewhere, then they're not eigenstates of SZ. But if we go back to the equations which we derived previously for these particles, right, there they are, right? If we go here, and if we are assuming that these particles are traveling only in the z direction, so px and py are equal to 0, right? So going back, right? Yeah. The rest, eigensets. This is not true for particles that are not at rest. However, for particles traveling in the z directions, then we do get, if we write it down, U1 of E and P is plus minus pz, or it's going to be 1, 0 plus minus pz over e plus m and 0. Of course, the same u2 is just 0, 1, 0, and then minus plus pz over e plus m. And then v1 is just 0 minus plus pz over e plus m. And 0, 1. And v2 is just plus minus pz over e plus m, 0, 1, 0. So these are eigenstates. This is it's not a general, right? It's a specific situation where the particles happen to be moving in the z direction. But in that case, then we do get that sz of u1 of e0, 0, pz plus minus p, right, is just plus half one half of u1. And of course, the same u2. And again, for the antiparticles, again, I look at the physical spin. So for antiparticles, we have a physical spin, which we discussed earlier, right? That the sz physical is a minus sz. And again, we have that sz physical part of v1. Again, antiparticle traveling in the z direction is plus 1/2 v1 e 0, 0, p. And that's z v of v2 e 0, 0 plus minus p is minus 1/2 v2. So for particles and antiparticles whose momentum happen to be in the z direction, these spinors do represent, eigenstates of the spin, z direction of the spin. Okay, but of course, the choice of direction of motion is extremely arbitrary. So we don't have to just, we choose the z direction as we wish, right? We can choose any direction that we want. So rather than defining states in terms of the external axis, right, g and z, which is external, it is much more natural to define them, the axis with respect to, the direction of motion, and that is the helicity, right? So the helicity. So the choice of direction is arbitrary, right? Rather, it is better to define helicity, h, as the normalized component of the particle's spin along its direction of motion. So it's basically s dot p, and normalization by p. So it is the normalized component of the spin in the direction of motion. Right. So using the definition of the spin operator, S, right, then we have the helicity operator. H, right, it's just sigma dot p over 2p. It's 1 over 2p. And here we have sigma dot p, 0, 0, sigma dot p. Again, it's a 4 by 4 matrix, right? This is just 0, 0, 0, 0. Okay. Two by 2 block form of a 4 by 4 matrix. What happened? Half of you got cameras off for some reason. Okay. What's the advantage of the helicity? It has several advantages. So we said one, it's much more natural to use helicity rather than spin, right? Because the direction of the z is just completely arbitrary. But we have something which is much more important, and that is that the helicity does commute with the Dirac Hamiltonian, while the spin operator does not commute with the Dirac Hamiltonian. What does it mean that they commute? That's a general question.
It is conserved.
It's conserved. It's conserved in time. It is not changed. All right. So if we measure the helicity at one time, it's going to stay. So helicity commutes with Dirac Hamiltonian well, free particle. We're talking about bound particles right now. So H Dirac and the helicity operator alpha dot p plus beta m is equal to 0, which means that helicity is conserved. That's not true for the spin operator. So there are Spinor states which are simultaneous eigenstates of both the Dirac Hamiltonian and the Helicity operator. Now, for spin half fermions, right, then by definition, the components of the spin measured along any axis, what are they going to be? If I make a measurement of the spin, regardless of which of any axis, what am I going to get? Come on, guys. If I'm measuring the spin. Okay, I have to admit that the whole concept of spin is one of those concepts that initially it takes you time to understand what it really means, because it's something which is kind of much less intuitive. You know, it's one of those things, you know, quantum mechanics in general is not intuitive. And spin is one of those things which are not really intuitive. When I say I have a spin half particle, what does it mean? I make a measurement of the spin. What do I get?
Half plus minus half.
Exactly. I always get plus minus half, right? I measure the spin in the z direction. I get the plus minus half, right? Okay. Now I'm somebody else wants to measure it, and you know you measure it in the x direction. What do you get? Plus minus half, right? Now it's in a different state. Remember that the z direction is something completely arbitrary. I cannot make simultaneous measurements. I measure once, forget about it. Somebody else comes to the lab, measures. We always see 1/2, right? That's the meaning of a 1/2 particle, 1/2 spin particle, right? That's what it means. So the component of the spin measured along any axis is always either plus half or minus half, right? So the eigenvalues of the helicity operator acting on the Dirac spinor are always going to be either plus or minus 1/2, right? So there are only two possible helicity states for a spin half fermion, either plus half or minus half, right? Again, spin half particle right, the component of the spin it's one of those things that, you know, I'm not supposed to spend time on them, but I see from your face that it's a good idea. The components of a spin along any axis, is always plus minus 1/2, right? So the eigenvalues of the helicity operator right, which acts on the Dirac spinor, right, they're always going to be plus minus 1/2. These are the only eigenvalues I can get. Right. So the two possible helicity states of a spin 1/2 fermion, plus or minus. So the two possible, or there are two possible helicity states for spin half fermion. And the names, they're called, you might know. Did anybody want to guess? It's not that because I don't know, I said 70% that you've heard it. You've heard the term. Anybody want to guess? I'm not going to hold it against you. No? Come on,
Are they called right and left?
Yes, very good. It's called right-handed and left-handed. Right-handed and left-handed. Well, these are the technical names, helicity states. Right. Now there is one important point here. Right, right-handed, this is with the positive one, lambda equal to plus 1/2, and left-handed is the negative one. I'll show it to you in a second. Now there is one important point, and you know, helicity is conserved. Once I measure the helicity once, it's going to stay there. But unless it is a massless particle, such as a photon, for a massive particle, helicity is not Lorentz invariant, because I can always boost to a frame. Remember, it's the projection of the spin on the direction of motion. Now, the spin is something intrinsic to the particle. Direction of motion is something that two different observers do not have to agree on. Right? I can see a particle moving in, if it's a massive particle, it was less than the speed of light, it can be moving in one direction. Then I can do a Lorentz boost to the same direction with a faster speed. And then from my perspective, the boosted perspective, it will be moving in the opposite direction. Now the spin would not change because it's intrinsic, but the helicity would change. So that means that the helicity is not the Lorentz invariant. Now I'm going to touch that, and I want to touch it today, so I'll have time because this is something which is important. The helicity is not Lorentz invariant for massive particles. It is for massless particles. Well, that's why we're going to introduce to you in about 10 minutes or so, or yeah, well, I hope, something which is called chirality, which is Lorentz invariant. Okay. and is related to the helicity. And in fact, the two coincide when it goes to the limit of mass goes to 0. All right, it's not Lorentz inverse for massive particles. Is that clear, this statement? Okay, now back to the question I was asked. So we can find the simultaneous eigenstates of the free particle Dirac Hamiltonian and the helicity operator. Let's do that, right? Simultaneous eigenstates of Dirac Hamiltonian and helicity. Operators. It's more algebra than anything else. So I just want to say, so I trust that you can do it by yourself at home. But no, let's do it. Okay. How do I find the eigenstates of the helicity operator? Right? Helicity operator times eigenstate is eigenvalue times eigenstate. Right? So helicity operator, I say it's 1 over 2p sigma dot p 0, 0 sigma dot p. And the eigenvalue, it's UA, eigenstates are UA, UB. Remember, this is a 4 component. It's written in a x, 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 which is just lambda UA, UB. Any questions? You guys got really quiet and okay, you're not interfering. Great, but I'm not sure that you understand. So there is nothing like interfering. I hate it when it's too quiet. Okay, let's continue the derivation. So we have basically two independent equations here, right? Which is just sigma dot p UA is 2p lambda UA, and sigma dot p UB is 2p lambda UB. That's great. Now we can do direct substitution. Let's wait because it's decoupled, right? We'll couple them in a second. Now you can do a direct substitution. And you'll find immediately that sigma dot p squared is just p squared. Do it at home. Guys, give me a break. I know that, if students are not given direct homework to prove, then often they don't do it. Do it so I don't have to actually give it to you. Actually, I thought of giving you homework today. I think I'm going to postpone it to Tuesday. I want to say because I'm lazy, but I don't want to say that.
We're recorded, so you know.
I know. Okay, direct substitution gives you that. So check it out, okay? It's written that it's recorded that I ask you to check these things out. And if you don't do it, then it's your responsibility. So, right, so if I do that, I just multiply by sigma dot p. So I get p squared UA is just 2p lambda sigma dot p UA. But sigma dot p UA is, again, I plug that in back in, right? This is just 4p squared lambda squared UA, which is just great because I have p squared here and here, which kills me, and that automatically tells me that I have the eigenstates or eigenvalues or lambda is 1/2. This is the right-handed, or lambda is -1/2. This is the left-handed. Eigenvalues. Eigenvalue, this is for the right-handed helicity state. For right-handed helicity state. Okay, so these are the eigenstates of the helicity operator, but we wanted to find simultaneous eigenstates. So that means that these states must also solve the Dirac equation. This plug these states solve Dirac equation. Right, gamma mu p mu minus m u equal to 0. Now I've already wrote that last time, or at least that's what I noticed to me. Let's see, when did I do that? Yeah, when we derive the, go back to your notes on Tuesday, or to the video, which is posted on the course's webpage, and you'll find out that we wrote down already that sigma dot p ua is e plus m ub. That was on the way to derive the solutions to Dirac's equation. So when we combine these results here with this result here, then we end up writing that ub is equal to lambda p over e plus m ua. Which means that the helicity eigenstate ub must be proportional to the helicity eigenstate ua. So if we are to solve that, right, solving means finding an explicit description of ua, then the easy is to use spherical coordinates. Use spherical coordinates. Right, p is p, then sine theta, cosine phi, sine theta, sine phi, and cosine phi, cosine theta, excuse me. And then we can write down the helicity operator explicitly. And then we have that 1 over 2p sigma dot p is 1 over 2p pz px plus I py, px minus I py, and pz minus. So if you just do it, you find out it's 1/2 and then sine theta, sorry, cosine theta, sine theta e minus I phi, sine theta e plus I phi, and then minus cosine theta. Okay. And so if I write down, remember UA has 2 components, right? Remember the solution is, you wrote down the solution, UA, UB. UA has 2 components, UB has 2 components. The 2 components of UB are linearly proportional to UA. And so if I write down UA is equal AB, and then the eigenstate equation, or the eigenvalue equation, sorry, then we got that the eigenvalue equation becomes cosine theta, sine theta, e minus I phi, sine theta, e I phi, cosine theta, minus cosine theta, or let's say cosine theta of A and B is 2 lambda A B. So again, we have a set of 2 equations, pretty straightforward. We get the upper line, and that gives the ratio of B over A is just 2 lambda minus cosine theta over sine theta E minus E I phi. Again, it's no more than algebra, really. So for the right-hand helicity state, we have lambda is equal to +1/2. So for right hand state, we have lambda is 1/2 plus 1/2. And so we have b over a is 1 minus cosine theta over sine theta ei phi, which we can write as 2 sine squared theta over 2 over 2 sine theta over 2 cosine theta over 2 ei phi is just ei phi sine theta over 2 or cosine theta over 2. And to save myself time, I'm going to simply write down as a capital S, which is just sine theta over 2, and capital C, which is just cosine theta over 2. And that pretty much tells me anything I need to know, because I know the ratio of B over A. I know the ratio of UB over UA, so the lower two versus the upper two. And so I can just write down that U spin up, right? It would just be C, which is cosine theta over 2, ei phi S, and then it will be the same multiplied by P over E plus M, C, and then P over E plus M, S, ei phi. And similarly, you get that the left-hand Helicity Spinor, which I marked down as a U down arrow, is just going to be minus S C ei phi P over E plus M S, and then minus P over E plus M C ei phi. So these states are both solutions to the Dirac equation and are solutions and eigenstates of the helicity operator. Now, of course, for the corresponding antiparticles, we have the V up and V down, and are obtained in exactly the same way. Just we have to use the physical spin SV is minus S. So for antiparticles, we use SV is minus S. And so for the antiparticle helicity up state, we have HV up is sigma dot B over 2P, right, V, which is minus 1/2 V up. And when you do the math, if, okay, honestly, this one I did not check. Normally I check all the equations. This one I just copied from the book, so I hope they didn't make any mistake there. V up is just P over E plus M S, and then minus P over E plus M C ei phi, and then minus S, and then ei phi times C. The V1, and just for completeness, V down, this is P over E plus M, C, P over E plus M, ei phi, S, C, and ei phi. Alrighty. It's a bit lengthy, but it was mostly just algebra, and just mainly to show you that there are these states which are, solutions to the Dirac equation and eigenstates of the Hamiltonian. Questions? Eigenstats of the helicity, Hamiltonian and helicity. Questions? Okay, let's see if I'm not going to rush too much. I might take a few more minutes of towards the end of the lecture, but if not, then I'll just complete that on next lecture. I'm going to do a tutorial, which is going to be a different subject, and then I want to start with a different subject. So let's try to finish now what we can. The last topic that I really want to discuss with you related to the Dirac equation is the thing which I mentioned earlier, which is called chirality. So I said the motivation is the following. Helicity is a conserved quantity, right? But for massive particles, it is not a Lorentz invariant. So what I'm going to do, I want to introduce another quantity, which is Lorentz invariant. But the price we have to pay is that for a massive particle, it is not going to be conserved. So it's not a constant of motion. For massless particles, such as photons, the two are coincide. So it's going to be the same. This is an internal parity. It plays a huge role in various branches of science, not necessarily just physics. And that's called chirality. Does anybody know what the name means? Where it comes from? Any idea what it is? You might. I just wonder if you ever saw this. Yeah, very good. So chirality is Greek for hand. Chiral something. I don't speak Greek. It's a Greek for hand, right? So it's a hand. The idea is the following. Your left hand is not identical to your right hand, right? It's a mirror symmetry, right? So it represents an asymmetry of an object, right? So for example, hands, right? A chiral object is an object whose mirror image is distinguishable from it, right? If you take your hand and you take a picture, and then you look at the mirror and you take a picture of your hands in the mirror, it's distinguishable. But if you take a sphere, a ball, and you look at the mirror, it's not distinguishable. It's fully symmetric. Okay. Now, chirality is a very important concept in various branches of science, not necessarily physics, right? For example, in the study of DNA, the DNA has a chiral, it's a chiral molecule. So, if you look at the mirror, it's not the same. It's a very interesting question in biology, why it is like that. If you can think of creatures, as far as I know, I'm pretty certain about that. The DNA of all living creatures on Earth have the same chirality. But it could easily, and this is a good question, why? Is this just a coincidence? It happened somehow when the first DNA ever was formed, or it is something else? I don't know. Of course, what we care about here in this course is not so much DNA, but the particle physics representation of that. So chirality, let me just state what it is. So chirality represents a mirror asymmetry of an object. It is an intrinsic property. And that's why it's a Lorentz invariant. Okay, so within the framework of the standard model, chirality in particle physics, in the standard model. Right, we introduced chirality by defining a new matrix. In case you hadn't had enough matrices, so you had 4 matrices: gamma 0, 1, 2, 3. So in order to avoid confusion, we don't call this new matrix gamma 4, but rather gamma 5. So we introduce a new matrix. It's called gamma 5. And it is defined to be the multiplicity of all 4 matrices, and I, just for convention, I, gamma 0, gamma 1, gamma 2, gamma 3. So again, if you go to the representations of the gamma matrices we had, and you plug in the values and you multiply the matrices, you end up that this matrix looks like that. It's a 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0. Or in 2 by 2 block form, this is 0, I, 0. And this is a 0, 0, 0, 0. It's big 0 here. Now, of course, it inherits mathematical properties from the mathematical properties which we already derived for the other gamma matrices. So it has certain interesting mathematical properties which make it to be quite significant. So it's easy to derive. So mathematical properties. Right, so we have gamma 5 squared is I, kind of automatic. Gamma 5 dagger Hermitian, of course it's gamma 5, it's all real numbers. But this is, it's all real numbers in this representation. If you have another representation like the whale or Majorana, it will be different. But still, the mathematical property of gamma 5 being Hermitian is going to stay. And it anti-commutes with all the other gamma matrices. The gamma 5 gamma mu is minus gamma mu gamma 5. Otherwise, gamma 5 gamma mu is equal to 0. That, by the way, is called the Clifford algebra, in case you encounter the name. It's the algebra of objects that anti-commute with each other. Now, the eigenstates of gamma 5 are called left-handed and right-handed chiral states. Okay, it's similar name to the left and right-handed states, which are eigenstates of the helicity. But this is called left and right-handed chiral states. So eigenvalues of the gamma 5 matrix are called left-handed and right-handed chiral states. And to distinguish those from the eigenstates of the helicity, we denote them by UR and UL. U right and U left. That's why I use the arrows to represent their helicity eigenstates. So, since these are eigenstates, then gamma 5 UR is plus UR. Of course, gamma 5 UL is minus UL. And then gamma 5 of VR, it's the opposite, it's minus VR, and gamma 5 of VL is plus VL. Now, in the limit of high energy, so E much greater than M, then we have that P over E plus M. What is that going to? What's it going to be equal to? Yeah.
P divided 2E.
Which is what? In this limit? Yeah.
Which is 1.
This is 1, right? Yeah, make sure that you convince yourself and you understand why this is true. So in this limit, the chiral eigenstates are the same as the helicity eigenstate. So for both particles and antiparticle spinors, right? So in this limit, UR is U up, UL is U down, VR is V up, and VL is V down. Now, what did I do here? Oh, okay. So now in this limit, then we have UR is U up is just C S E I phi C S E I phi, right? It's a limit, right? And UL is just minus S C E I phi S minus C E I phi. And VR is just S minus C E I phi minus S C E I phi. And VL is just C E I phi C S E I phi. Now, one comment here is that although the the spinors UR and equal to VL, UL is minus VR, they would still represent different, it looks the same, but they still represent different states of particles and antiparticles because there is also the spatial part. This is just the intrinsic part. Now there is no simple physical interpretation for the property of chirality. Right, so chirality does not have a simple physical interpretation. So if we compare between helicity and chirality, the comparison, basically saying that for massive particles, right, helicity is not invariant under boost. Right. But chirality is. Because it's intrinsic. Right, and the way to say it mathematically, right, is just because this gamma 5 matrix is just, again, a matrix of constants. So just numbers multiplying a Lorentz transformation. However, right, helicity commutes with the Hamiltonian, so it is conserved in time. But the gamma 5 matrix does not commute with the Hamiltonian. So the eigenstates are not conserved in time. Right. Okay. There is one last thing, but it's going to take me another 5 minutes, so I think I just do it on Tuesday, not to run too much overtime, which is the projection operators. I'll just complete that on Tuesday. Any questions? Any questions? Yeah.
Between helicity and chirality, which one is more useful, or is it dependent on the situation?
Depending on the situation. I told you that initially I told you there are several representation of the gamma matrices. There is we use the Dirac Pauli representation. There is also the Weyl representation, and the other name of the Weyl representation is the chiral representation, because it's most useful for chiral eigenstates. So it depends on what you're trying to measure. I think the main idea, I think in this course, it's, the main purpose is that you be aware that these things exist, and we make some use of those. Obviously, conserved quantities are important when it comes to calculate which processes occur and which not. Right? The chiral eigenstates. Okay, I'm not sure, so I don't want to just say things which I'm not sure about. But they are there and they are useful for various things. But I'll try to be precise on Tuesday. I'll give you a few examples of where they're used.
Thank you.
Any other questions or comments? Okay, so I won't give you homework today. I'll give it to you on Tuesday. And yeah. Have a nice and safe weekend. It's supposed to be a nice weekend. And I'll see you all on Tuesday.
Thank you.
All right.
Thank you.
All right.
חג שמח.
חג שמח לכולם. Stop sharing. Let me do the stop recording.